Welcome to Calculus 1. In this video, we're going to talk about what we so-called the infinite limits. So, if I would define what an infinite limit is, an infinite limit is referring to a function in which the f of x, the y value increases or decreases without bound as x approaches to c. Alright, I used that phrase before as the function increase or decrease without bound. Alright, that's referring to what we so-called infinite limit. But make sure we understand that if the limit of a function as x approaching to c is equal to infinity, that does not mean that the actual limit does exist. It actually means that the limit doesn't exist. Okay, it's just that when we write infinity, we just represent how the limit failed to exist by denoting the unbounded behavior. Okay, so whenever I wrote infinity or negative infinity, okay, all I'm doing is writing down the unbounded behavior. The actual limit does not exist. Okay, so for example, I already grabbed this function for you as well. If I have a if I have a function 3 over x minus 2, find the following. I want to find as x approaching to 2 from the left hand side and x approaching to 2 from the left side and 1 from the right hand side. So I already draw this picture for you. This vertical line here is my vertical asymptote at x equal to 2. So as x approaching to 2 from the left side, my y value or my function actually decreases without bound. Okay, it actually keep on going downward. So that tells me that as I'm approaching to 2 from the left side, the unbounded behavior will be negative infinity. Alright, as I'm approaching to 2 from the right hand side, my y value actually increases or goes up higher and higher and higher. So the unbounded behavior will be infinity. Okay, and we can do that by graphing the function 3 over x minus 2, and what I'm going to show you is I'm going to pick a number on the right hand side, coming from the right hand side of 2. Okay, let's make it as small as we can, maybe like 2.00001, and my y value is 300,000. So as I'm getting closer to 2 from the right hand side, okay, my y value actually increases without bound. That's what that means. Let me rewrite that 2 again. That's a 2. Alright, so a formal definition of limits, of infinite limits: let f be a function that is defined at every real number in some open interval containing c, except maybe at c itself. So the limit of the function as x approaching to c is equal to infinity. What that means is for each m that is bigger than 0, there exists a delta that's also a positive, such that the f of x is greater than m whenever my c is my x minus c, or my c is actually between 0 to delta. So graphically, what that means is, alright, my limit becomes, my limit will be, we will denote the limits of the function as infinity if there exists a number m. Okay, this m is a y value that is where the y value of my function is actually bigger than that. So that means what? That means there is a lot more y value that is greater than my m, such that wherever that m is, there exists a c that's in the interval of c minus delta and c plus delta. Okay. Alright, so that's what the theorem here is saying. Alright, similarly, okay, I will denote my unbounded behavior as a negative infinity as x approaching to c. That means there exists, or for each capital letter n is another y value that is actually a negative. Less than 0 means negative. Then there exists a delta that is a positive number, such that all the y value for my function will be less than that capital letter n whenever my c is in the interval of c minus delta to c plus delta. Okay, so of course the distance between c to c minus delta is the delta itself. Okay, so we talked about the definition of limit before. Right now I'm just having another y value, capital letter m or n, okay, to kind of help me to explain it, my infinite limit. All right. So what can happen is, as my y value m is getting, as I move out this blue line upward, my delta will actually begin to shrink. So that means I'm getting closer to approaching to the c. And eventually, if I move this thing all the way up to infinity, okay, eventually I'm actually evaluating my x value at c itself. Alright, so let's take a look at these one-sided limits. The limits of natural log of x squared minus 16 as x approaching to 4 from the right hand side. Let's see what's going on here. Natural log of x squared minus 16. Alright, I want to graph it first. This is what it looks like. I need to approach into 4 from the positive side. Alright, kind of look kind of weird. By the graph, it seems like my y value stop it right here. So let me go to second calc, number 1 value. Approaching to 4 from the right hand side. So I'm going to pick a number that is very close to 4 from the right side of 4. 4.00001. My y value is actually negative 11 something. So as I'm getting closer, my y value will actually decrease without bound. So my answer will be negative infinity. Okay, that would be that's how I denote decrease without bound. Alright. I'll try another example. I believe this one I can actually redefine my function. So if I want to redefine this function, let me factor the top and the bottom. Let's see what happens. Alright, so the limit of my function as x approaching to negative half from the positive side. 6x squared, I can use 2 and 3. 1 will be 1 and 1, of course. To get a positive 1 in the middle, I got to have a positive 3x in the inner and a negative 2 on the outer. 4x squared, I can use 2x and 2x. And my last term here is 3, so that'll be 1 and 3. To come up with a negative 4 in the middle here, I need a negative 6x on the outer, positive 2 in the inner. Or positive 2, yeah, positive 2x in the inner. So I can see the 2x plus 1 will cancel out. So my redefined function will be the limit of 3x minus 1 over 2x minus 3 as x approaching to negative half on the positive side. Let me just graph this redefined function real quick. (3x minus 1) close divided by 2x minus 3. Alright, this is a rational function approaching to negative half on the positive side. So negative 0.5. I think I am defined at negative half. Negative half is over here from the positive side. So let me do negative 0.499999 as close as I can, which is 0.625. And negative 0.625. Excuse me, positive 0.625. If I convert it to a fraction, that would be 5/8. Very good. Alright, so my limit is 5/8. Okay, at negative 0.5, I'm actually already above the x-axis. That's why my answer is positive. Alright. Now let's take a look at some of the properties of infinite limits. So let C and L be real numbers, and let my function f and g such that the limit of my function f as x approaching to c is infinity. The limit of my function g as x approaching to c is L. Okay. So let's think about this. If I were add and subtract the two functions, one of them has a limit that's infinity. The other one is a particular number. So if you think infinite plus a number, that got to still be infinite. So the sum and difference of these two functions will be infinity, because one of my function already has a limit as x approaching to c is already infinity. Same thing if I will multiply, of course. Alright. Same thing if I will multiply. But that's assuming L is a positive number. Now if my L become a negative number, so let's say this limit is a negative 1. Alright, negative 1 times infinity, of course, that gives me a negative infinity. Alright. If L is a positive, positive times infinity is still going to be positive. Now this one is very funny. The quotient of the limit here. Remember now, g of x, the limit of g of x is a particular number. So let's pretend that's to be a 2. The limit of my function f as x approaching to c is infinity. So as you can see, if you take a number divided by a real big number, okay, when you divide it by a real big number, you're actually going to be very small. Okay, that's why the answer is 0. Think of it in terms like 2 divided by 10. It's 0.2. 2 divided by 100, 0.02. So if I keep on dividing by a bigger number, okay, if I keep on dividing by a bigger number, I'm getting what? Smaller. Eventually I will become 0. Alright, that's the reason why this answer is 0 here. Alright, let's find the limit of this problem. This is not a one-sided limit. Alright, because I'm adding here, so I'm gonna split up. I'm gonna split this up and look at it from this perspective. So that's assuming this 1 is a f, this 1 over x squared is my function g. So let's think about it. The limit of 1 as x approaching to 0. Okay, the limit of any number is that number itself. So that's 1. So that's like an L here. Alright, the limit of the other function, 1 over x squared, as x approaching to 0. If we graph it, 1 over x squared. Alright, as x approaching to 0 from either direction, positive or negative. Okay, my function increases without bound, so that will tell me it's infinity. Alright, so 1 plus infinity, the limit for one plus the limit of the other whereas infinity will still equal to infinity here. So my answer is infinite. Alright, let's find this one-sided limits. We talked about cotangent x before. So if I will graph it again, I'm going to graph for the cotangent x. 1 divided by parenthesis. Cotangent is inverse of tangent. Oops. Alright. Now, as x approaching to 0 from the positive side. Alright. X equal to 0 is here. As x approaching to 0 from the positive side, I'm actually increased without bound here. So I know the limit of my cotangent of x as x approaching to 0 from the positive side is increased without bounds, so that will denote as infinity. Alright, the limit of 3 as x approaching to 0 from the positive side should still be 3. Alright, so since this limit is a positive 3 times infinity will still tell me my limit for the entire function is increasing without bound, infinity. That would be this one right here. Alright, so just a couple examples on the property of infinite limits. And that will conclude this video. Thank you for watching.